Welcome everybody to the fourth and final installment of the Philosophy Department, London Public Library Joint Venture, Philosophy and Climate Change. I think everybody here, have you signed one of these waivers?
I haven't. Awesome.
Okay, yeah. Good, good. Thank you for doing that. And if you have friends who were on camera in previous weeks and who didn't sign a waiver, if you wouldn't mind taking them home, that would be great. Otherwise, we can't use the footage, and we'd like to, because part of the whole point of this discussion, the point of these things is discussion to be honest. Wait, so today we have Lenny Smith from the London School of Economics and Erica Thompson, who is actually in the other London, I think, at the moment. And they're in the public doing climate science in the dark.
So I just want to start. The idea here is this question, the difference between sort of weather forecasting and the light. It's a kind of science in the light, and climate is science in the dark. So there's a different kind of sort of forecasting you have to do, but it's not a question of what's reliable and informative. So this is a very nice paper from 1950 saying probably there is no other field of applied science in which so much money has been spent to so little effect of real progress as weather forecasting. Right? Now, not many people would say that today about weather forecasting. Right? So he goes on, as a practical reality, it appears today to be quite as distant, useful forecasting, as when Richardson tried to work on it in 1922. And that's just turned out not to be the case. You know, science advises to provide actionable information really pretty fast, sometimes. And in this particular case, right, in far less than 30 years, that would have been the mid-'80s, right, weather forecasts were extremely valuable, absolutely worthwhile. But he also points out the failure, Erica's back. Oops, Erica's gone. The failure was doubtless caused in part by his efforts to deal with all the variables at once. He wasn't able to see what the sources of his errors were, Richardson. And that was true for Richardson in 1922, and that's a little closer maybe to being true for us with climate science today. So this is about doing science in the dark. In theory, the little e's here means that Erica is actually here electronically, but she's not. This is the thing about postdocs, you know? Okay, so let's get started. This is a very hard to see picture. Could someone hit one of the front lights? So this is a picture outside my airplane window on the way here. This is Greenland. And basic science can tell us a good deal with not very many observations. For instance, if I look at this picture, I can tell it was daytime. You think the wind is blowing? What direction? So I'd suggest the wind, you see these clouds here? I'd sort of suggest the wind is blowing air up over these clouds. So the wind is sort of blowing in this direction and lifting this air. I'd suggest that because this is all dark, we're probably looking in the summer or fall. And I've been doing this trip for 20 years. I haven't gone back yet and figured out exactly where all the photographs were. But I think 100 years ago, a lot of this was white. I don't have the data to back that up. And that's part of the problem, right? When we move to longer and longer time scales, it's harder and harder to verify what we think is going on. Now, the reason for showing you a picture of the airplane is I can now ask Erica why she isn't here yet. Right? And Erica isn't here because Erica doesn't fly. And I can't remember the year, and if we get her back, she'll tell you why. Erica hasn't flown for something like 8 years. Okay? And although there's lots of questions about climate science, climate change, and how big the changes will be, right, our uncertainty, right, or not our uncertainty, our insights into that change are enough for Erica to decide not to fly and to more or less deal with the professional issues of flying or not flying. Yeah, you want to? I'm happy to wait a second. You want to switch? Switches that?
You want lights on? Can we put the lights on? Or not yet?
Yeah, I mean, lights on now would be great.
Lights on, great.
Okay, so that's Erica's first contribution. What are the odds? What are your odds? This is what science is all about. What are your odds on getting Erica back? 50-50. Okay, good. Okay, so this is the sort of thing that Erica and I want to avoid. Okay, this bus this is actually also hard to read. This is a bus stop. This is actually a picture of the sign, and what the sign says is the predictions are wrong. Sorry for any inconvenience. We particularly want to avoid this sign coming up half an hour after the bus was due. This doesn't really inspire confidence or a good feeling about using the bus forecast system. And when can that happen? When does sort of predictive science really lead to bad decision making? And I'm going to suggest that we have three, eventually four, but initially three different cases. One would be, say, when technology is lacking. When we don't have the technology to actually use what we know, I mean, we know what to do, it's just that if we try to do it, it takes us 5 days to get a half-hour weather forecast. And so we can't really use the information we have. A second one is when the science is lacking. We actually believe something that is false, or we know that we don't know. So when that's the case, you know, can we actually know that? I want to argue we can know that. And the last one is sort of political shenanigans. So I'll give examples of all of these. So while I'm talking about climate science, there's really much, much broader implications. So this is a Latour. I don't know if you can quite see it. These are a bunch of, this is a physicist, a mathematician, a philosopher, and a statistician playing cards. The test at the end will be who is who. But technology lacking would be this guy who happens to have all the money and is very neatly dressed. Technology could be lacking if he can't do the calculations. He doesn't have a hand calculator to do the calculations to work out what are the odds of him having a good hand. Right? Science lacking would be if he doesn't understand enough statistics to figure out what calculation to do to see if he has a good hand. And political shenanigans would be this guy who is actually looking at you and even knows he's in a painting is drawing aces of diamonds out of his belt. Right? So these are different limitations that stop us from being able to make good forecasts. Now I'm going to talk almost exclusively about probability forecasts. Even when I'm trying to figure out if Eric is coming back or not, I didn't ask him a yes or no question. Okay? So some people think this is a cheat, right? When you make probability forecasts, you could never be wrong. So that's not really quite true. This is a graph from NOAA this morning of likely tropical cyclone activity in the southern Atlantic, or in the mid-Atlantic. Here's Florida. We're up here somewhere. I grew up there. And what they're trying to do is say, with this blob of clouds and this glob of clouds, this has a 20% chance in the next 48 hours of turning into a tropical cyclone. And this one, I think, says 30. Oh, actually, that's not from this morning. That's from yesterday afternoon. That's last night. This guy's gone down to 10. This is this morning, and this guy's disappeared off the screen. So no longer worried about that blob, but this blob is still at 30%. And the idea is, if you're trying to make decisions about the next 2 days, this gives you an idea of the chance that this blob of clouds is going to spin up into a tropical storm or a hurricane. Now here's a better example. I gave a talk like this 2 years ago almost exactly, and this really did happen right as I was running into the talk. There was no activity at all. 8 hours later, we had a 10% event. And then as things went by, the 10% event, oh, we got one with 20. This is every 8 hours. And suddenly we got 0. What's that? We had a 0% chance that this would turn into a tropical storm. Now, you know, I remember the weatherman when I grew up in Florida, and he never, ever would have said 0% chance. Michael Fish famously failed to warn people about very high winds in England. You just don't say 0% chance. So as my talk was coming up, well, it went away. But then it came back. 10%, 20%, 50%, right? 50%, Tropical Depression 16. and Hurricane Patty. So in this sense, a probability forecast was for sure wrong because you said there was a 0% chance of something happening, and it happened. So the first rule is never say 0 unless it's impossible, and never say 100 unless it has to happen. Okay? But you can do other things as well. So you can go through and take all the times you forecast 20% and ask, how many times did the thing happen? And if the relative frequency, if you forecast 100 things at 20% and 20 of them happen, that's about right. And the way those numbers balance out, well, it won't always be right on this diagonal. It won't always be exactly the same. But these error bars sort of give you an idea of how well you can evaluate probability forecasts. And as long as it's inside the bars, in a statistical sort of way, you can't fire the guy for having made a bad forecast. Of course, when I hadn't realized, but I actually erased this 0. It turns out that when the National Hurricane Center in 2012 forecast 0, about something like 20% of the things still happen. You might ask why they forecast 0 at all. So that's probability forecasts. But that's not the difference between science in the light and science in the dark. The reason this is science in the light is not because they tend to be good, but because we have the outcomes to evaluate them. Right? In 1 year, you can make 20 or 50 or 100 forecasts of things that might turn into a tropical storm, even if only a few dozen do turn into a tropical storm. So that means you can actually evaluate your probability forecasts with relevant observations when you're making them. You can learn from your mistakes. They no longer make quite the same forecasts. I'm still waiting to see if they'll make a 0. So here's another case where we use probability. So these are constants of physics, and they tend to change. But when a physicist gives you a constant, well, they're two different kinds, right? You can have a constant like Newton's constant, big G, and that's got a bunch of numbers, and this little thing in brackets is an uncertainty estimate. And then you have some, like the speed of light, which can't change. That's because this is exactly the speed of light. This is how we define meters per second now. So we've taken out the uncertainty by making this a constant. So these first 3 can't change anymore. But if you look between 2006 and 2010, Newton's constant, well, it not only changed, but the uncertainty got bigger. So that's perfectly good science. We study something hard, we understand it a little bit better. It's possible that our uncertainty is actually going to get bigger, and it's extraordinarily common in all science that we often underestimate what our uncertainties are. Nothing here really about climate science or weather forecasting that's different. What's different is every few years you get a new little handbook, little blue book if you're a physicist, has all these numbers in it, and as far as I can tell, the numbers, most of the numbers that are changing now really don't matter very much to people who aren't doing really hard calculations but already have them on their computer anyway. So last year, there was a big storm in England, on just the other side of England, in Europe, called the St. Jude storm. And what's cool about this storm are these forecasts are made 10 days in advance. So these are different forecasts for the same day, made with slightly different models. So these are all cheap models, and that's a very expensive model. That's actually the best model in the world. And what you see, even 10 days in advance, there's a storm, there's a really big storm, there's a storm, they're in different places. But many of the different models, ensemble numbers, I might say golf balls by mistake, right, give you the same information. They all warn you that there's a storm. Now, what actually the forecast looked like was this. 10 days in advance, we had all these forecasts. Some don't have a storm, some have a storm, some have a storm so big, a storm like we've never ever seen. And at this point, I get to say, so what do? I want a probability. I count the number of little doodahs with storms. I divide by the total number of doodahs, and I get the probability of a storm. And Erica says, no, you can't do that.
No, you can't do that.
Thank you. Now, will you explain her thesis? So Erica's thesis is about looking at changes in storms that move across the Atlantic under climate change. And she talks about something she calls the hawk moth effect. So the butterfly effect is why we have to do this. In fact, the mechanism, the mathematics behind this were created by Ed Lorenz, the same guy who came over to Europe and helped them code it up back in the early 90s. So every day, because we don't know exactly where to start, we start from 51 different places and watch them all go forward. And they spread out. But in this case, 10 days in the future, lots of them still said there would be storms. Well, Erica, why can't I just count them and divide by the total number? And the answer is, because the model's wrong. I could, but if I drew that graph, there'd be lots of times I have a storm where there were no storms, and there'd be too many times I had 90% storms where there were no storm. And sometimes there was a storm when there was no storm, right? The point is the model isn't right. The model isn't perfect. It's extraordinarily useful. Seeing this 10 days in advance, right? The Met Office, I think, didn't make a big general announcement until 6 days in advance. It gave people a lot of time to prepare for a storm, which might actually, maybe the storm actually ended up happening somewhere over Norway or somewhere up in the North Sea, somewhere where it wasn't so important. But it didn't. It gives us good warning. It doesn't give us sort of nice probabilities that we can maximize our expected utility, those things that Rotman was talking about last week. Right? But it does give us a lot of insight and information. That was Erica's speech. So, okay, so when we move to climate, we have to ask difficult questions, right? Questions where we really can't see the outcome. And the point, I think I can get some of these in green. Let's see. The point is other people have to do this too. So people who take care of nuclear arms, people who are designing ships for the next America's Cup, people in national intelligence, people in reinsurance, they're faced with a situation where they're really only making one long-term forecast. And by the time, they can't make the same forecast over and over and over and learn from their mistakes, which was, Erica was just explaining that to you a minute ago. They can't learn from their mistakes the way that we can here. And in fact, we can't even quite do statistics the way we teach people to do statistics in Statistics 101. We have to violate what's called good practice. So sometimes people yell at climate scientists for violating basic statistics, but you don't have a choice. If you're going to answer a question which has to do with something 50 years in the future, you can't just sit around and wait, right? Sometimes these violations are required by the nature of the problem you're trying to answer. So this is one of my favorite philosophical terms, a brute fact. I'd never heard of a brute fact before I started talking to philosophers. It's a brute fact that climate models, well, we throw them away every 5 or 6 years, but they're making 50-year forecasts. So we can't see how they get better or even how they work. In the way that for a weather model, we make forecasts every 12 hours and we keep the same one for a couple of years. Okay? Hi, Erica.
Hello.
There's an ensemble of Ericas right now, and you're about to get big, I think. So I've actually already explained some of the things, but I haven't really said very much about the hawk moth effect or about your thesis in storm tracks. Do you remember that one?
Okay.
Your thesis? It wasn't that long ago.
I remember.
So you know what I'd ask you to do now. So I'll just ask you bluntly, right, straight up, is I looked at a bunch of different weather forecasts for the St. Jude Day storm, and I talked about how I would like to just be able to count the number of forecasts with storms and divide by the total number of forecasts. So why can't I do that?
Well, if our model was a good model, but it was just inaccurate, then we could count the storms, and we'd hope that that would be a good representation of the total amount of uncertainty in it. But we know that our models aren't perfect. After all, lots of people are being paid to improve them, and when we improve the model, we expect that we might get a slightly different answer. But occasionally you might get a radically different answer. And the good thing about a model like the one that you just showed is that we can test it day after day, so we can actually see whether it does a good job or not on balance over time. But for a climate model, we don't have those tests, so we need to be more confident about the basic physics of a situation in order to have confidence in an output like that. So in this instance, you probably could do that, but only if you were to test it over time and see whether or not it was biased.
That's exactly what I said. But I didn't explain the Hawk-Mock effect. So I did talk a little bit about the butterfly effect in chaos, meaning that things spread out. And so that's how I actually got those individual little weather maps. What's the Hawk-Moth effect?
So as you might expect from the name, it's a bit like the butterfly effect, but it's a bit more camouflaged and a bit more ugly. So the butterfly effect, hopefully Lenny explained, is when you're trying to predict something, but you can't measure the initial conditions perfectly. So you can't measure what the situation is like right at the beginning of the thing that you want to predict. And that is really a solved problem, as hopefully Lenny's demonstrated already. But there's another difficulty that you might run into, and that's that you might actually have got the equations wrong. You might have got the model wrong that you're trying to use to make the prediction with. And when that happens, then you can have the same problem of a very small error in your representation, causing a much larger error over time in the thing that you're trying to predict. So that's what we call the Hawk-Moth effect. So it's a little bit like the butterfly effect, but it's more, a bit more subtle and a lot harder to deal with.
Bigger, nastier, and not as popular.
Yeah.
Yet.
Not as pretty.
Maybe, probably not as pretty. More interesting for science, less interesting for statistics. Okay, thanks, Erica. Just in case.
Okay, I'll try to stay here.
Okay, so there's one thing we do know, right? I mean, the guys in green here are the people that we talk to at CATS, the Center for the Analysis of Time Series, right? One thing that's really clear to me, hard to see without the lights, but maybe you can make this out. Doing science in the dark doesn't suggest that scientists have gone over to the dark side. Okay? You can take a quick glimpse, and if it's too frightening, we can go back to the lights.
Mr. Harper?
This is another one of my postdocs. No, this is one of my students. No, this is one that didn't become my student but went to another place. Right, so it would just be shameful to sit quietly 50 years waiting to test your climate forecast if you actually had a forecast that suggested there was a real risk of very bad, dangerous things happening. And at the same time, when we move to doing science in the dark, because we can't test our models every day the way we do weather models, the nature of the evidence we get is weaker. Okay? And last of all, just to be clear, the physics underlying the assumption, the theory, the claim that CO2 in the atmosphere initially starts warming the planet, this is about as good as it gets science. You can't claim it's perfect, you can't claim it's true, right? Science doesn't do truth. But it's as good as it gets science. And that's enough for Erica not to have flown since, when's the last time you were on a plane?
2008.
2008. 2006, I think I guessed, was close. Okay, so what I want to claim is that this scenario is really nothing new, and we'll get rid of that guy for a minute. I think you can hit the lights back on if you would. Or maybe not. So what I want to do now for the next 15 minutes is walk through the history of science, a couple of different stories, and try to show you where this sort of thing happens over and over and over again. Unlike weather forecasting, we can't really generalize from those examples, but I think it's still useful to take the air out of a lot of claims about the relevance of climate science to the real world. So it was a dark and stormy night in 1707 when a dispute came out between the captain of a ship and a sailor, his navigator, about where they were. The claim is they hung the navigator. But there's no record of whether this really happened or it's just a myth, because 2 days later, the ships hit unexpected rocks. We lost 4 ships, 1,400 sailors, including the captain, and the ship that ship that the guy was presumably hung from, and all the records about whether this guy had committed, it's not treason, it's not mutiny, but he basically tried to tell the captain what was going on. So this is our third example, right? The failure of forecasting through political shenanigans. It can be the case that forecasters are at personal danger, they may be vulnerable professionally, It just may be costly to really stand by your forecast. 50 years later, there was another disaster on the south coast of Wales, the UK, with the loss of hundreds of lives as a result of this, because the sort of indications of the storm had been seen at other coastal stations. Fitzroy, captain of the Beagle, started collecting telegraph messages that came into London and trying to watch for places where the pressure was dropping so we could issue storm warnings. He coined the phrase weather forecast, but he was forbidden from actually making forecasts because they were thought to be like prophecies, they didn't have any scientific basis, they blah, 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 blah. Okay, so he goes back, he tries to figure out how to do this. He partners with a guy named Leverrier in France. Now, Leverrier was already very famous because he had predicted the existence of Neptune using equations. We'll come back to Leverrier in a minute, but Fitzroy, meantime, he's getting all this resistance in England. He doesn't know who it's from. It's sort of coming from the Royal Society. It turns out it's coming from Galton. We know that now. Right? But let's go back to what this resistance was. This is by Fitzroy in around 1862, and he notes that objection has been taken to these forecasts when he's trying to say that there's likely to be a storm somewhere in the west, because the storm can't go everywhere in the west. Right? But an idea of the kind of weather thought probable, almost probability, right, can't be otherwise than acceptable provided that the person getting it is in no way bound to act. So he's not trying to give orders or make decisions for the decision makers. He's trying to give them information so they can make better decisions themselves. And he claims that accurate interpretation is the real deficiency. This is just a wonderful phrase. If you look at how it works now in terms of understanding what climate models tell us, or even what weather models tell us. And speaking of weather models, this is a map from the UK Met Office that says all these counties are at risk. This is exactly what people were complaining that Fitzroy was doing. All this is saying is that there's a 30% or more chance that something nasty is going to happen in one of these. It's not saying it's going to happen in all of them. Right? So that kind of problem is still with us. We've connected Fitzroy and Leverrier. For those of you who didn't take high school astronomy, Leverrier is super famous because he sat down and he worked out that there's a planet outside Uranus's orbit. Uranus wobbles a bit. You look at Newton's laws, it says there must be a reason, because Newton's laws are perfect. So we get a planet outside Newton's laws. He figures out where it has to be to make the wobble that he sees. He has some German look for it. The German finds it, and this is the discovery of Neptune. He gets everything, right? He just gets everything you could get as a French scientist at the time. But he didn't quit, right? He was still fairly young. He kept going. A few years later, he went back. He started out looking at Mercury. He goes back, he starts looking at Mercury's orbit again. And it wobbles. And knowing Newton's laws are right, he figures out there must be a planet inside Mercury's orbit. And then this guy, French this time, so it must be true, right, finds the planet on the 26th of March, 1859. Leverrier goes to visit him. Everything is documented. Huge celebration, although, of course, we expect that kind of stuff from science now, right? So this guy was awarded the Legion of Honor, right? This wasn't like, no one really believed this, blah, blah, blah. But there is no Vulcan, right? There's a big X here. It turns out Newton's laws don't work very good really close to the sun. Well, actually, they work extraordinarily well, but they're not perfect. Okay? And this is the kind of problem you get when the science is lacking. There's no, well, I don't know, could he have known? It doesn't really matter, right? The point is, when we go beyond what we really know, when we push our understanding, our current understanding too far, we're likely to make this kind of mistake. So now we have Leverrier and Vulcan. I want to bring in Whitehead. We got Einstein in there too. So Alfred North Whitehead, he was sort of looking at all this in the 20s, sometime later, and he came up with this fallacy of misplaced concreteness. And I won't read the quote, but it's a great quote. The reference hopefully is up there, complete with the page number. Right? What he more or less says is it's really good to think about abstractions because you can't think about everything. But your modes of abstraction, actually, if you take these 2 pages and substitute model for modes, you can almost republish it about weather forecasting or climate, right? So it's of the utmost importance to be vigilant in critically revising your models of abstraction. Sometimes it happens the service rendered by philosophy is entirely obscured by the astonishing success of a scheme of abstractions in expressing the dominant interest of an epoch. So he's talking about 100 years or so of Newton's laws. You might think about computer simulation all over the board in the last 10 or 20 years. It's just lots and lots of stuff you can do. Okay? So, Galton. So I want you to be careful. We don't want to believe our models, but as he says, they're extremely useful at the same time. Jumping back to Galton, this is actually the very first weather chart, the first weather map ever printed. It was in the Times on March 31st, 1870 something. And it sort of shows what's going on around England and France. They no longer cut off foreign countries like they do today. I don't know why. Okay. So the thing about Galton, though, who knows who this is? Anyone recognize this photo?
Darwin.
That's Darwin. You haven't seen this lecture before, have you?
No.
He's not a plant, although he is a student. Okay, so this is Darwin. What's Darwin's connection to Fitzroy? Fitzroy was the captain of the Beagle. What's Darwin's connection to Galton? They're cousins. And Fitzroy was giving Darwin a really hard time about evolution and how old the Earth was and whether or not there was enough time for the Earth to. And maybe Galton was sort of giving Fitzroy a hard time because he was Darwin's cousin, right? And that's actually not, was Fitzroy just a crazy guy? Well, not really. If you look at someone like Lord Kelvin, at this point in time, Lord Kelvin was much younger, right? Kelvin would have come down on the side of the Earth is not going to be hundreds of millions of years old because the sun can't burn that long. So the science was really much more open. And I think there's a little bit, I think now actually there is certainly evidence that it's known that the problems the Royal Society was given Fitzroy were coming through Galton. It's not known, of course, exactly why. Okay, so Galton also invented the Galton board. And this is a sort of cool thing. These are pictures of them. So the Galton board, the idea is you drop a piece of lead shot. It actually works better if you pour a whole lot of lead shot, which is why it looks like this. And it hits a nail, and it has a 50-50 chance of going to each side. And then you look down at the bottom, and you end up getting a Gaussian. No, so you get a normal distribution. We don't want to name things after Germans. So the term normal distribution was used in the UK. And that all sounds great. It sounds nice and nice, but it's randomness. I mean, is it really random? What do you think? So we can ask this sort of question. At the time, maybe we thought, is physics, is it fundamentally random, or is it just because we don't know enough? And Laplace invented this demon that knows everything. He doesn't, not like an omniscient being would know everything. He can actually calculate everything. So he has perfect equations of motion. He's got noise-free observations. He knows exactly where the piece of lead shot starts. And he has unlimited computer power. He can actually approximate it so much that it's not even an approximation. And the uncertainty is less than the size of the lead shot. But we can't do that. So in 2007, in this book on chaos, which is available on Amazon Canada, we get the Demon's Apprentice. So the apprentice, she has perfect equations of motion, but she doesn't know exactly where to start, and she has unlimited computer power. So the best she can do is a sort of ensemble forecast like we saw before. She looks at lots and lots of different initial conditions and follows them forward. But her model's perfect. She can make probabilities you can bet on. Our model isn't perfect. We're like the novice down here. And this is the sort of problems we have to deal with, right? Our models aren't quite able to do things perfectly. So let's go on to weather forecasting. Lewis Fry Richardson, he was interested in forecasting May 20th, 2010. He did it. He finished sometime during World War I, toward the end. So it took a long time to make this forecast. The forecast was really, really inaccurate. It was a bad forecast, right? But after he'd done it, he could look back and see what really happened, and he actually managed to make progress. So by making a huge investment in his model and moving it forward, he actually worked out what he did wrong. And even today, using really new weather models, You can't quite, I don't know if you can quite see this or not, but this is a volcano. This is a very tall mountain, a volcano. You see there are these cool little swirls and stuff, vortex shedding behind us. Our models can't do this. We can see lots of stuff our models can't do yet. So that's still the case. We're sort of at the edge. The important thing here is that we get to see what our models do, and then we can see what their limitations are. And Richard could even work out what he'd need to do in order to forecast weather faster than it happened. These are computers, graduate students. Actually, at the time, they were professional computers. He worked out that with 64,000 people sitting in an auditorium like that, putting pieces of paper back and forth, parallel processing, he could compute the weather faster than it happened. He couldn't do it in 1922 because he didn't have the technology. But he thought he had the science, and he thought he understood the ideas that he could have pushed forward. Right, now we've got just about everybody. The one thing I want to leave, we have examples of limits from science, limits from technology, limits from political shenanigans, and back at this point in time, it was alpha male overconfidence. This idea of just pushing things forward because you're right. Okay? That one will come back up again later. And the question is, like, how would we see the difference? We know we're not the demon, but maybe our equations are, they're not perfect, but they're close enough that it doesn't really matter for a 100-year forecast. How do we tell the difference if it's in our equations, if it's chaos, no, sorry, if it's in our initial conditions, if it's chaos, my thesis, or if the problem is in our actual equations, it's the hawk moth, her thesis. Okay? Well, let's think about the NAG board. What's the NAG board? The NAG board is not a Galton board. So it looks sort of like a Galton board. This is it. That's a little bit bigger than real life. This is a golf ball, so it's pretty close. Right? So can you see that? It's a bed of nails. There's a white pin here, and they're alternating rows of nails offset precisely halfway across. I have dropped 1,024 golf balls from precisely the same initial condition immediately below that white pin. Okay? Why? Because I want to make a forecast of well, I don't want to say quite what I want to make a forecast of. Let me just say that I've dropped, this is a subset of 1,024 balls that give me a probability distribution for predicting with the NAG board. Now I want to test my predictions, right? These ensembles are really good in terms of telling me everything that can happen for the NAG board. And I want to draw a parallel. That's why I sometimes call these guys golf balls. A parallel between these model forecasts and the golf ball distribution. And of course, there's a problem. This distribution tells me about the uncertainty within my model. But reality isn't a golf ball. So reality is a red rubber ball, which is a lot like a golf ball, but not quite a golf ball. So then what exactly does this distribution of golf balls, my model, tell me about the one time and only time that I dropped the red rubber ball? This is the real weather. And this is NAG weather. Of course, every day I drop it from a slightly different place. But I can still see where the red rubber balls go and see where the golf balls went. I can try and understand what my model does well and not. I can try and learn from my mistakes. The NAG board here is doing science in the light. But climate is different, right? Climate, I'm making a 50-year forecast. Things will be different. Climate is like dropping a yellow rubber duck through the NAG board. I've never seen the yellow rubber duck. Right? Something is different when I move out into climate change. The atmosphere is different. The way things work is different. And the sort of best I can hope for is all the different colored golf balls and kinds of golf balls that I drop. They sort of agree in distribution. They give me some information about what might happen with the yellow rubber duck. But until I've seen a rubber duck, I'm extrapolating. Right? And you know, the American Statistical Association has a T-shirt. I wish I don't have one. It says, "Friends don't let friends extrapolate." But you have to extrapolate if you're going to try and do the climate problem. You don't have a choice. Now, this is known. These risks are known. This is from the AR4, the last IPCC report, and it says, you know, these limitations imply that distributions of future climate would be wider if the uncertainty due to structural model errors were accounted for. So it's not like the IPCC denies this, right? But it's really difficult to try and talk about how to make decisions unless you really embrace it. So here's a typical graph talking about the different kinds of uncertainties for a 25-kilometer grid box in the southeast of England. And they talk about internal variability and uncertainties in the carbon cycle, structural uncertainty, parameter uncertainty. The one I really want to focus on is this idea that our models aren't quite right. This is the Hawk-Moth effect. And the problem with that is we only have a lower bound. We've got lots of golf balls and rubber balls and tennis balls. We have all these balls. We don't have a rubber duck. We wouldn't even know the rubber duck was the right one if we did. So all we can get here is a lower bound for this uncertainty. The real uncertainty really might be much, much bigger. So what do, right? For all we know, this piece of the pie could be bigger than the rest of the pie. So it's hard to figure out how to make quantitative guidance about how to make decisions. We know today that our model probabilities aren't mature. If we knew nothing, we have no new science and no new observations, but a vastly bigger, 2060s, 2100 hardware computer, we would expect our probabilities for a 25-kilometer grid box to change. In that sense, our probabilities aren't mature. And all I'm really trying to do here is just discuss, again, the IPCC knows this, they say this, right? They don't make the mistake of confusing our golf balls with reality. But when you go to try and interpret it in terms of what to do, of how to make plans, it gets extremely difficult. So it's sort of data everywhere and not a bit, these are bits to bank on. We have models everywhere, but they're not really adequate to answer the detailed kind of questions we'd like them to answer. That doesn't mean they can't inform our decision making. We can think, well, maybe it could look like a rubber panda. And how would a rubber panda be different from a golf ball? Or how would a rubber piano be different from a golf ball? Or, right, we can try to think out things and work out what's the probability that our models will have gone badly wrong, that they might be misinformative. The IPCC puts this at 10 or 20%, depending on what you look at. And do we know where that uncertainty lies? Is it because we've left out things that would make the Earth hotter? Or we've left out things that would make the Earth colder? Or do we not know, maybe equal to the same? Do we actually understand? We can think about these issues. And we can also ask the question, how fast are we going to learn about this? And what's the potential cost of not doing anything? After we've done all that, then each of you, each individual one of you, can take your particular appetite for risk, and maybe it's the risk of people in the future, but it's still your appetite, and you can decide what you want to do. At that point, the science is done to the point of it's trying to give information for decision making, and the decisions have to come based upon, well, I actually have a really big appetite for my great-grandchildren's risk, or I really want future generations to be able to enjoy the swamp that I enjoyed when I was a boy, which will be under seawater almost certainly no matter what we do. Okay, so we can learn from other groups that do work in the dark, and often these groups, they really embrace model inadequacy more than we do. So this was a question someone asked. I'm not sure if I actually asked the first question, but the issue was, let's suppose we drop a ball from a tower. We estimate how long it takes the ball to hit the bottom. And we get a bunch of physicists together, like 8, and we estimate how long it takes a golf ball to fall, a bowling ball, a basketball, a wiffle ball, right? A rubber duck. How long does it take to fall? And someone took this seriously. Dave Higdon at Los Alamos, right? They're really worried about unknown unknowns and known unknowns and known unknown knowns and all those things. So he got together an experiment. What I didn't realize is how serious these guys are. First of all, they don't drop it from the top of this tower. They drop it from the bottom of this tower down a 1,000-foot shaft. The shaft is called UA1. It's in Area 1. Right? Area 51 is just up here off the map somewhere. We dropped 2 bowling balls, 3 basketballs, 2 golf balls, 3 wiffle balls, no rubber ducks. I'm not sure why. The sheets of laser light detectors, right? Really accurate measurements. And here we are standing at the bottom, and remember that basketball. Right? That is one of the basketballs which was dropped I don't yet have the data about where it is today or whether it's still around. Okay, so this is a question I ask MSc students, and Erica runs this whole series of workshops on understanding uncertainty. How good did we do? Normally I have a picture of us. Oh, you could see us all there, right? We are not gender balanced, but we're not gender unique either, although you can't really tell in this picture. These are literally the people, right? We spent a day trying to figure out how this was going to go. So how accurate do you think we were? Normally they have little clickers. You don't have to answer the question, but just think. Were we less than 100th of a second? Was our error less than a 10th or a second, or less than a minute or more than a minute? This is for a basketball with an initial 0 velocity, dropped 1,000 feet from down the tower with timing which is to a fraction of a second, which I don't have the security clearance to know how accurate the timing was.
Did the tower have air in it?
Sorry?
Did the tower have air in it?
Yes, there is air. It was in the air. Absolutely. Good question.
Let's take a poll. How many people think A?
Take a poll. How many people think we were less than 100th of a second? Okay. Less than a 10th of a second. Less than a second. Your accuracy within a second. Less than a minute. And more than a minute. So my statistic, you generally fall about up there with really, really good undergraduate scientists, right? Or even young career graduate scientists. The numbers haven't been declassified yet. It actually took them 6 months to do this picture. But I did get a summary, and now I even have a short film, which we may see afterwards if you want to stay, right? I couldn't have made up data this good. The bowling ball was completely destroyed. One of the basketballs failed to make it to the bottom. We never thought that it could actually, it's pretty obvious, right? I mean, the shaft is about as big as this room. It's 1,000 feet. So there was a note somewhere, one of the miners found it. So someone rappelled down, and oh, there's a basketball, so it's stuck in the side of the shaft. Okay? So for me, that's a big surprise. That's when something my model couldn't do turns out to be important. So we thought surface roughness, the dimples on the basketball, right? The things on the golf ball, the lack of the things on the bowling ball. We thought this was really our dominant uncertainty. And sometimes, if we had thought about it more, if we had the right people in the room, we might have been actually able to estimate this probability of a big surprise, but we can't do it inside our models, right? The whole point is the model, it's the things that aren't inside our models are the things we really want to understand. Okay.
Turn the lights off if you're going to do a video.
Do you want to see the film? It'll take us another 3 or 4 minutes.
Sounds great.
It's worth seeing. Yeah. Okay, hit the lights. Actually, the sound effects, I think, this is the first one. They drop the ball. You see these little pieces keep coming down for a while. And then being Los Alamos, here's one in slow motion. No, that's right. But it's the prettiest part of the experiment, right? That's right. So we weren't really trying to figure. The sheet of laser light is above this board, and that one, if you notice, that one which has although they're sort of disturbingly large numbers of little bits and pieces of other stuff, that wasn't there when we were at the bottom of the mine shaft, right? This one, which actually comes out, this is the one that. Well, so I don't know. What should I do, right? Should I be curious at how well we did for that ball? which clearly made it everything was okay? Or should I say, well, it doesn't really matter that we were within 0.5, 0.03 seconds for that ball, because there's some where we just made a fundamental error of the dynamics of the entire process. Right? But again, this at least was science in the light. Because Higdon and these guys took an experiment that may well win one of those horrible awards that are given out sometime for people who do expensive experiments. Right? Because they did it, we could see. If we had gone on talking, it could have been months or years, several PhD theses, before someone like Erica says, oh, what happens if the ball hits the wall? And then suddenly we change everything. The fact that we can do the experiments, that's what we mean by science in the light. So then to conclude, I'd just like to talk a little bit about political shenanigans. Do we recognize this guy? Right, do you hit the lights? Or we can leave them off. I don't know. You can decide.
I like them all because I can see it.
So this is Prince Charles giving the weather forecast for Scotland. This is just fun. This isn't real shenanigans. But this is something interesting. This is a list. This came up last week. This is a list of 400 prominent scientists disputing man-made global warming claims in 2007. Okay. Now, there are a number of things about this list that I find really interesting. One of them being that it only has 387, according to Wikipedia, distinct names on it. It doesn't actually have 400. But the other thing that I found disturbing at first is that I'm on it. Right? And then I began to sort of like this list, not because I was on it, because they more or less give my quotes. They say, this is why I'm on it. And I think I'd stand by most of those quotes. And then I found out there were some other people who were on it, much more famous than me, and that I respect greatly. Whether you call these false positives, or you say, I don't think there's anything really that I'm quoted saying that I haven't said here tonight. Right? So you get into this issue of this discussion about how much you have to say to be on a list like this. There's a lot of divergence of views about details of climate science or how much we can take away from our models, but I'm in very little doubt. I can't say positive because it's a non-science statement, right? But the basic idea, the basic underlying physics of CO2 in the atmosphere warming the planet, starting things off, that's as good as it gets science. And I imagine there are quite a few scientists of the 387 or however many there really are who feel the same way. So let me leave you with a question. I'm from Florida. We're walking together in Florida. And we find you've been bitten on the hand by a snake. We didn't see the snake, but if it was a deadly carbon black snake, this is the deadly carbon black snake, the bite is going to kill you in 15 seconds in a horrible, nasty, painful way, like in the movies, unless you cut your hand off. And Erica has a hatchet. And you have 5 seconds left.
4, 3, 2, 1.
Did you cut your hand off? So who cut their hands off? Wow. So usually it's about 30-70, yes. And sometimes, once, with a bunch of scientists, it was about 50-50. And when they saw it was 50-50, everybody was surprised. There was this wonderful goes through the crowd. Okay? Now, the point of asking this question is to make, the risk is real. There are lots of risks that are real. We don't have probabilities for the snake. We don't have information on the relative. There are lots of questions you can shout out, but you only got 15 seconds. And when the risk is real, refusing to decide is a decision. Deciding to wait and not act is a decision not to act. If you have the belief that you're going to get a lot more of information on a time scale which poses very little threat to you, it's a completely relevant decision, a rational decision to decide to wait. Okay? And happily, with climate change, we had more than 15 seconds. But we spent a lot of that time already. So, science in the dark doesn't imply science has gone to the dark side. It does mean that we can't appeal to the unreasonable effectiveness of science done in the light, because we don't get that level of update and information coming in. And at the same time, when we have science that really can't be falsified, without risking catastrophic effects, we need to be careful how strong we present that compared to the basic science, like CO2 traps infrared radiation, which is extraordinarily strong. We want to make this clear so that if we have to take these arguments apart someday, we can see where we want to stop and how we went wrong. So just to summarize then, what are the limits to good scientific support and decision making? Well, one of them is technology is lacking. What does that have to do with science and the light? Well, if technology is lacking, then for science and the light, I think we have a lower impact, right? We couldn't actually do this with human beings. It meant a delay. I couldn't decide whether my bus was going to come or not. Actually, this bus was going in the other direction. I had to cross the street to take the photograph. So it had no impact on me at all. The Met Office has a brand new giant supercomputer. And it's still, we know now, before we start, won't get the physics we need to say what's going to happen in London in 2100. So announcing that we are somehow going to answer that question yesterday morning on Radio 4 might not have been such a good idea. In the light, this is fairly low impact. In the dark, when we have to end up backtracking, I think we really get a larger medium impact. What about the sciences lacking? Well, science in the light, we predict Vulcan, we look at for it for 30 years. By the time general relativity came along, a lot of people had doubts. Some people had very serious doubts whether or not Vulcan was really there or not, right? Galton drew this weather map. He didn't have the insight to try and integrate this forward in time. So again, we have a lower impact when we're doing science in the light. When we're doing science in the dark, this lacking science can have a huge impact. Our best available models, the best answer we have, can be inadequate, and we can know it's inadequate. Right? And the question is, how do we present it in that? If the best available isn't adequate for purpose, what do we say? Right? And finally, political shenanigans, whether it's people playing cards or people going to the dark side or people being related and complaining about things which are actually done now. I mean, this is extraordinarily dangerous. So for science in the light, this is still hurtful. They hung the poor forecast, right? This guy was right? And for science in the dark, this hurtful plus, it's not only hurtful for us, right? But it's hurtful for generations to follow us. It's hurtful with a very, very long shadow, if in fact it's done in a way that suppresses the sort of things that we know. Okay? And what about, to be politically correct, this is alpha person oversell and overconfidence, so that Erica can be overconfident and oversell too. Well, for science in the light, this is just what we have to deal with. Science has always dealt with this, right? But again, for science in the dark, that kind of dynamic which pushes forward bad ideas, not on their scientific merit, and in some sense knowing that they couldn't possibly have the scientific merit of science in the light, right? That's also deadly plus. So that's us thinking that's the basketball that we'll never see again. This is the iceberg that sunk the Titanic. And this is sort of London probabilities for the future. We know now that we really shouldn't push these as if they were the sort of probabilities like for raining tomorrow. Thank you very much.
Okay, let's have the lights back on for questions and comments. We have time for questions and comments, but before we begin, let me just mention, both of you came in late. We have been told by the library that we can't use the footage of the discussion sessions unless we get you to sign a waiver, and I see some people who actually did say things in previous weeks. So if you wouldn't mind, if you don't mind having the video of you from the discussion sessions put on the web, if you please sign these. Martin, can you, I see a few people. Okay, questions for Lenny? And if you do object, then just tell Greg, and he'll leave you out.
And through the marvels of technology, if you don't want to ask me, you can still ask Eric.
Yes, Eric is still here. We're there. Yes, sir.
Just a curious question. What happens to these models when you interpolate instead of extrapolate? How verifiable are they? I've always wanted to ask someone who actually does it.
This is a great question. The question is, suppose we actually, instead of trying to extrapolate, we try to interpolate with these models. So this whole notion of extrapolation is pretty clear because we're changing parameters in CO2 we've never looked at. Interpolation is a little trickier, even for weather models, because we're still sort of extrapolating, but at least the parameters are staying the same. When we take weather models and we go back and we try to interpolate the weather in the sense of making hindcast, forecasts of what we've seen before, the weather models tend to do about the same as they do when we're forecasting. We can often go back and say, hey, look, if we make this observation different, the forecast gets better. But that really hasn't been studied in a really detailed way. It's very common. If we miss a storm, actually we rarely miss a storm, but if suddenly a storm appears with only a day or two before it's going to happen and we've never seen it, we often go back and say, oh, look, if I change the middle of the ocean and make it colder, the storm appears 3 or 4 days earlier. Now that's sort of testing the interpolation, and it's sort of just cheating, right? For the climate models, though, it's different. For the climate models, if we go back and we look at how well climate models do in the last century or over the last 50 years, they generally look okay, but there's really quite a wide range of systematic errors across them. And there's huge discussions about how important those systematic errors are. It depends a great deal on how you interpret the model.
So can I
Please.
So do you keep aside sets of data essentially to validate the models? Is that part of the modeling?
So it's not. You want to answer that? I would say in general, I can't tell where to look, but it's not in general. What it usually happens by accident. So very often, some of the data doesn't get in time for the weather forecast, and their time is set by the television stations. So we sometimes have data we can go put in after the fact and see the difference it makes. We sometimes discover new data, like taking all the Royal Navy ships and taking all the captain's logs and working out what the weather was in different places as you go around. There are attempts to go back further in time, but while that is a real scientific enterprise, it's tricky in that the problem was important enough that, and the experiment wasn't designed by statisticians. So all the really good juicy data, if we could use it, we probably did use it. And in any event, we know, everybody knows roughly what happened. Everybody knows there was a big El Nino in 1998. It's sort of impossible to unknow that. And I think that's really a difference with science in the dark, where we can't undo.
So there isn't a purposeful collection of a data set that could be used to verify?
There is an ongoing collection of data. It's not as organized as it should be, and I think, in fact, we're missing a lot of very important data, which we can never go back and get again. But as those programs are generating data, it usually then goes in, right? So in terms of going forward, there's attempts to verify the models, to evaluate the models. Going backwards, there's attempts to find new data. But there isn't a systematic way, there isn't a systematic program, as I was saying this afternoon, what I'd like to do is to take all the climate modelers and put them in space stations, different space stations, and then not let them talk to each other, and then give all of them most of the data, but not the same data, do exactly what you suggest, right? And then I'd have all the data and all their results down on Earth, and I could make that kind of evaluation. Right? But that hasn't been done yet.
Thank you for the wonderful presentation. I was just wondering if you could, or somebody that's in the crowd could confirm some knowledge that I've gained and had repeated to me in the past, but you had Einstein's photograph up there predominantly. I'm in solar energy, by the way. My name is Sonny James. If you go to my website, it's Sunny Newswire. You can catch my information there, and it'll tell you more news on solar energy. But I just wanted to confirm, Sunny Newswire, just Google it and you'll find it there. But I wanted to ask you if you could confirm this for me with Mr. Einstein's photograph there. I understood that Mr. Einstein was the one who told us many years ago that if we are left without no birds, which are being killed off by the windmills, and no bees that are being killed off by Monsanto and the chemicals, and he said that if we're out without the birds and the bees, we have 4 years left.
So I'm not aware of this statement, but I'd be happy to try and look and see. I mean, he looked at a lot of different things.
Yes, he certainly did. Well, that was confirmed by another person about, I think 3 weeks ago to me, and I just wanted to...
Since you asked, what tends to happen is like when someone says something important, but then they really regard it important, it often gets attributed to someone more famous than actually said it. It's hard to trace that one, but those who have looked at it, it probably doesn't originate with Einstein. But you know, that's not the point because it's important, and you know, no matter who said it. You know, without the
Einstein saying it is much more important than some other writer.
No, I think in fact, I'm not going to answer this one. Okay. I was going to segue into, I'm more interested in the facts of the matter than who said them first, and Erica keeps bees.
Yes, so I'm actually a beekeeper, so I'm really interested in this. But I think that there are a whole lot of stresses on the bee populations at the moment, and the chemicals is only one small part of that. And it's obviously very clear that they're an important part of the ecology of the whole system. I don't know whether the 4 years actually is a meaningful number or not, given that there are lots of other pollinators. I guess if you suddenly took out any keystone species, you would expect that to have a big effect.
Okay, so I mean, I think the really important point is that, you know, we can sort of decide that our background assumption is that the system is extremely robust to perturbations, and we really don't, you know, the probability of anything going badly wrong is very small. Or we can worry about the fact that maybe, in fact, we're not robust to perturbations, and even what looks like fairly small changes could have feedbacks that have a very large effect. And the problem with science in the dark, right, is the only way really to figure out that that's the case is to try it and see. Right? And so you have to have a really big appetite for risk to keep pushing things further and further because they haven't broken yet. Right? Was there another question over here? Yes.
Well, it touches on that, like appetite for risk. When you ask the question about this, are we cutting the egg or not? One important piece of information that we need in order to know if really this is likely that we're going to die is how many of those snakes there are around.
Is how
many of those snakes? What is the prior probability of having those snakes? And that matters in the decision. What would be the equivalent for the Islamic model? So I take it this being an analogy, what should we be doing? It's urgent or not? Something bad might happen.
So
if we have an equivalent of what is how frequent the snakes are in the region.
I can't tell where Erica's camera is. But I don't know if she heard the question either. So
I couldn't quite hear the question.
Okay, so I mean, the things like with the question with the snake, are you saying this depends a lot on our prior beliefs, or are you and the question is how should we try to change those, or are you saying it?
Should we cut the end or not? So
right.
Your decision will depend.
So my take. Yeah. So it's going to be something about developing. I'm going to let you do the climate one. I'm just going to do the snake because I'm the one from Florida, and in England they don't really have snakes. So what about the snake? I find the answers to this question say a lot more about your risk appetite than they do about your prior beliefs, although in some Bayesian sense they should tell you something about both, right? I think the issue is we're often faced with very little time to try and develop, build a good prior. It always sounds a little odd thing to do. We don't walk around with priors in our heads on things we had never thought about before. And so the balances, I think, have much more to do with we make a classification of some very, very general thing, and then we say, this is like that. Yes, I jump out of an airplane. Right? I mean, I haven't done the cross statistics on, but I've tried actually doing on how well they do betting on different games. Sometimes they do well. Actually, the people who win very often cut their hands off. Okay, so what about climate? I'll try to answer this while Erica's thinking, and then she can give a better answer, as she does. So for climate change, for me, we've got lots of models which are informative. They're informative in a qualitative level. I don't think we can get a lot of quantitative information out. But they all show bad things happening, right? Net negative things happening. We can't really tell where, but and if you just think about the world changing however it changes in a significant way far from what we've actually adapted to and are used to, then locally at least you would expect local hardships. And so then the question to me becomes more one of, is it likely to be a large magnitude change or a small magnitude change? And once it changes, is it likely to accelerate? Can I think of things to push it back? And maybe there's one or two, but they aren't really strong. But there are lots of things that would make it accelerate becoming even warmer. Right? And just that general analysis is enough for people with a low risk tolerance to say, I don't want to do the experiment. On the other hand, it's not irrational for someone with a high risk tolerance to say, sure, I'll do the experiment. I mean, I don't think there is a should in there quite the same way. I think you can balance off what you take from the models. My personal belief is that that if we continue emitting carbon dioxide the way we do today, there will be a large change in temperature and it will stimulate large positive feedbacks. But I don't want to go further than that because I want to try to stay on the side of discussing the science to inform decisions, not trying to use the science to motivate you to do something different. Right? So Erica, so was that roughly the right question, or do you want to ask Erica a different question? Do you want to respond to that?
Sure. I mean, from my point of view, I think that I'm also quite skeptical about the abilities of models to predict detail in the future. And so my confidence in the basic physics of climate change is really what motivates me to, say, make personal decisions about not flying. Things like the physics of the greenhouse effect, really, that's been known for 100 years. It's not something that we can easily contradict in any way. It's something that we can say we're really confident about. And then we can take that to warming, and then we can say if we change the heat balance, the energy balance of the Earth significantly, which it will do, then we can expect that to have a strong influence on circulation patterns in the atmosphere and the ocean. And that because those are what determine our weather, we can then expect the weather to change significantly. And because we are adapted well to the present weather, in most cases, then we can expect that any change would probably be negative. So that's really my point of view on that. And then there's also the question of what you're actually, I mean, what values you have about the future change as well. So for instance, my choice not to fly could be seen by some people as being career limiting or in some way a welfare cost to me, but I don't particularly see it like that. I'm quite happy not flying. And so if there are actions that we can take that are sort of win-win on both sides, it seems silly not to do them.
Excuse me if I may, Miss, I was interrupted by a security guard when you answered the question about the bees, and I didn't hear your answer. I was wondering if, with your wonderful work in bees, are you being influenced in England as well as we are here in Canada and North America with respect to the pesticides from Monsanto in your country as well, and in Europe?
Sure, so there are, I mean, I don't want to hijack this talk into one about bees, but I mean, yes, there are pesticides in Europe, and some of them have been banned by the European Union. But I think, I mean, of course, we've got to remember that there are lots of other stresses on the bee population as well, which include destruction of habitat due to monoculture, agriculture, the reduction in the number of beekeepers, other pests and diseases, and those are all really more important than the pesticides, I would say.
Well,
but the fundamental.
I agree with you with what's happening in Canada and North America at this time.
Okay, so I think that the fundamental thing the fundamental thing that sort of ties it back in is that although it's on a shorter time scale, the sort of bee issue is not dissimilar in that by the time bees or frogs or by the time we get good data that something has wiped out the bees, we can't sort of then go back and undo
Yeah,
it,
too
right?
late.
So we can't do a good enough.
You can't from a London, Ontario law firm that is suing them, Monsanto companies for $3 million.
The point is,
with respect to the problem.
excuse me. The point is, we don't have to win that argument.
We do have to. If the Monsanto is true,
Please,
then we have 4 years
Sonny,
left.
please,
4 years left. if we have
Sonny,
emergency
Sonny,
needs.
please let him finish, thank you.
Oh, I'm sorry. That's
Thank you.
trying to
We
defer
don't
this
have to
conversation.
win the legal argument about causation to take a risk management approach and avoiding doing the experiment in the first place, right? The time scales are such that if you don't want to take a big risk about X, you can avoid, and you can put in X, you can put whatever you want, right? You can actually, you can make a reasoned decision based on your risk preference not to do an experiment which would lead to a potentially irreversible outcome, whether it's a kind of technology, whether it's a kind of wildlife, or whether it's the climate of the planet.
And a question in the back there.
It's more of a political question in the sense of, I'm curious, what has the fact been amongst people like yourselves of the politicalization of science? Climate science has been thrown into the political world, willingly or unwillingly. I guess money has come your way. I'm curious, what's the effect on the quality of science, the culture of climate science? Do you have anything?
So again, unfortunately, I have a really good dodge for that one. Just like I don't know what the Earth would have been like if we hadn't put CO2 in the atmosphere. I don't know what climate science would have been like if we didn't have this combination of heavy-duty pressure and different kinds of funding and focuses on funding. I would certainly argue it has had a large and dramatic effect. And some aspects are positive, some aspects are negative.
Do you have concerns then?
I have a talk about how we manage to keep quality science going in a situation where people are driven to do very specific things, kinds of science, and I've seen several young scientists, I think young postdocs, some might have been students, be very aggressively questioned in public talks in England when they weren't even really talking about the political and mitigation issues of climate change. They were talking about some benthic foraminifera, and the extremely aggressive questions, accusing them of lying, of being part of a mass conspiracy. And if I got questions like that when I was a graduate student, I'm not sure I would have. That's not. So it has. Some people then. This has lots of effects. This is. I think that's probably the sort of thing I wanted with my alpha person. I don't have a drug now for it, but this is the issue. I mean, it certainly has an effect. It leads to some extent, it leads to a circling of the wagons among the scientists, which is bad for science. It leads for sometimes, the things that I was quoted for, I pointed out that we haven't, as a community, climate scientists are not always as openly critical now as they have been in the past. If you read climate science in the 80s and 90s, there are beautiful statements about the limitations of the models. Those are said in much more coded language now. They're personal attacks of people chasing people's personal emails. This has to have a negative effect. And I don't know how that balance really works out. Maybe this is another good reason to send them to the space stations.
They were doing it last night, but it blew up.
So I like the idea of the hawk moth effect and just errors and problems with the models, but I wondered if you could apply that concept to the grand savior that I think a lot of people are waiting for, at least in North America, which is a technological fix. So do our models have any ability to tell us what would happen if we implemented some large-scale geoengineering fix, or is it all hawk moth effect when we get to?
So it must depend a little bit on the particular fix, but right now our models vary by 3 degrees in the Earth's global mean temperature. The different models have very different Earths, and they all have a similar response when you increase CO2. So there's sort of this, so the way I say it is planets not all that much like the Earth, all warm up about like we've seen, and that's actually cause for the fact to believe it's a robust relationship. But when you go down to trying to say, well, what if I X, then those kinds of experiments, they're still pretty challenging even with weather. So we do experiments with weather where we say, hey, I've got a couple planes, I'm going to fly them over the Atlantic and take extra measurements just at the right places. And then we try to do that kind of experiment, and those experiments are very hard to interpret. So believing that we could see a small difference would be quite hard. And I'm turning around and she's already got her hand up. Go ahead.
And also, there are geoengineering modelling projects which look at what happens when you put mirrors in space or you change the albedo of the deserts and that sort of thing. And what they generally find is that although you can indeed cancel out, say, 2 or 3 degrees of global mean temperature, actually that doesn't really matter because nobody was ever killed by global mean temperature. Nobody cares about global mean temperature. What people want to know is what the climate will be like at their particular point. And that's what the models have difficulty doing even for any given, just for the normal climate change, just by putting the CO2 in the atmosphere. And so when we try to sort of cancel it out and add on something else on top, we can cancel out that one-dimensional measure of global mean temperature, but you end up with a planet that actually looks totally different. And when you look at different models and different planets that look totally different, but what you certainly can say is that the geoengineering methods that have been proposed don't act as a direct cancellation out of putting CO2 into the atmosphere.
Right. So I guess I would disagree slightly on the question that was so early on. I think I've forgotten. But there's an issue of what we want to know. I think that's really the question. They certainly differ on what the impact in places would be. We don't. The local weather, I don't think we're going to know that. So, but that is the thing that impacts us. And I think Erica's argument goes through in terms of the way they would change the local weather is really the issue. And right now we don't get the local weather very good. So to look for changes in the local weather. So Erica's thesis is actually on storm tracks going across the Atlantic. I don't know which way. Okay, so storm track, where the storm, and when you start changing the models, the storm track doesn't change very much, and that's because it's been nailed there like the Norwegian blue in the Monty Python sketch. They don't change, or they do change? They don't change.
Well, so
why don't they change?
Do is when you make a small change to the model, sometimes actually this is a really good example of the hawk moth effect, and you find that when you just change the top level of the atmosphere slightly and move it up a bit in order to represent more of the stratosphere, which we previously thought wasn't really important because there's not actually that much air up there. When you add that in, you get a result which shows that the storm tracks, instead of being predicted to move northwards towards the pole, they actually come out with a different prediction and say it will move southwards towards the equator. So it's a great example of where even just quite a small and seemingly insignificant improvement to the model physics can actually end up giving you a first order difference in the output.
Right. And so the sort of take-home message is, again, we don't really know the impacts, what they will be, but we have reasonable evidence to think they could be large, and do we really want to find out? I mean, there's a completely, it's a risk management decision-making process. We have good reason to believe that that there's no way to use the models to say things won't happen, and the basic physics suggests things would happen too.
Yeah, I'm not sure. I heard on CBC Radio quite a few seasons ago that Britain and Europe has become up much better at predicting seasons versus Farmer's Almanac, which many people use here. I'm wondering, is there any check to that?
So I haven't actually done tests with the Farmer's Almanac, but I have done tests with sort of models statisticians build, which for a climate modeler is pretty close to the Farmer's Almanac. So very, very simple models that don't include the laws of physics, right? Seasonal models, right? So I do this for weather models. I do this for seasonal models. I do this for decadal models. And if I had data to do it for 100-year models, I'd do it there too, right? And for the seasonal models, for some places, the actual today's seasonal models do a little bit better than the empirically based models, the models that only look at the data and the physics only comes via the data. But they don't do spectacularly better, but they do better. And I'm sure my models do better than the Farmer's Almanac, I hope. So, but I haven't actually done that test. So the bottom line is the physics models on seasonal scales do a little bit better. It depends a lot on where you look. Right? The physics-based models don't do tremendously better. On long-term forecasts, the two are really pretty close to being the same decadal forecast. In short-term forecasts, the laws of physics blow away the statistical models just utterly and completely. And that starts to fade out as you get out around, in general. If you don't, in general, that starts to fade out around week 2 or so.
So in Ontario, what sort of season should we be expecting over the next fall and winter? Should we be expecting another? So
in fact, I've never looked at this London, but one of the slides I took out was for Southwest England, where they're really looking at probability distributions and trying to see them shift back and forth. And we claim, and the Met Office provides those forecasts, and they're being documented, and we're writing them down. But right now, there are not very many of them, and so it's sort of hard to say. We've only got a handful of evaluation data to look at. So we're back into this question of, how do we actually look at that? Right now, I can't really tell. The seasonal forecasts are still very wide. So if I just, suppose I collected, so I'm interested in Ontario, I look back at all the Novembers for the last 50 years, right? And I look at the temperature in November, and then I'll get sort of a distribution of Novembers, November temperatures. That sort of makes sense. So if I don't know any more about this November than I know from knowing all those last 100 years of November, no, that doesn't work.
Well, yeah.
This is the thing I want to do better than. This is my statistical equivalent of the Farmer's Almanac. So what I do know already is that when we then go back to make a forecast for 3 or 4 months ahead, the width of that forecast is pretty close to the width of all those November. It's not like I have a really sharp forecast for this November and a really broad forecast from my Farmer's Almanac historical statistical Novembers. So if this was really sharp, then in a year or two I could tell whether or not it was accurate, because I'd have to keep hitting inside. But because they're similar, it's very hard to pull that information out.
Well, would a farmer make his predictions to how to look after his farm based on the season coming ahead? Should he still go out by Farmer's Almanac, or is there other better sources out there?
So I certainly think I would look at both, not the Farmer's Almanac, but my statistical model. As long as they were both free, I would look at my statistical model, and I would look at the Met Office seasonal model. I would look at both. The UK Met Office, I don't know who does your forecast, but if the Met Office, their model does it, I don't know if they actually put it up. They do it for the UK, I would look at both.
Eric, did you have your hand up?
Yeah, but I forgot. Sorry.
Anybody else who hasn't asked a question yet?
You.
Well, I can hug
Erica, you got a question?
Wait, brief comment?
Yes, if I may, I believe in what Mr. Einstein said is true. I had it confirmed, as I mentioned a few weeks ago. I'm in solar energy, Sunny Newswire at Google, and I'm just in the process of launching a Kickstarter campaign, and it's called Solar One. I can use all your assistance. It's going to be a solar-powered ship. We're going to design the ship, state-of-the-art. We're going to have it powered by solar energy, condo on board. It's going to be, if you'd like a nice condo, let me know. We're going to have the biggest dance floor on the planet on the ship, and it's going to be sailing around the world as the ambassador for solar energy around the world at Kickstarter in the very near future. I tried to buy from England the ship that was the Invincible a few years ago. They got back to me right away from England, from the people that were wanting to, they had torn out the engines. I thought, perfect, we'll put some solar engines in it. And they sold it to Turkey and they scrapped it. So I wanted to save the Invincible, but we'll do the Solar One and we'll get her launched and we'll have some fun, and we'll save the planet, because I believe what Mr. Einstein said, we have 4 years left for killing the birds with the windmills, and they're flying into windows downtown London and Toronto by dropping like rain, and the bees are, as you know, Miss, are being killed all over the world by Monsanto.
Well, I hope you have a great voyage.
Okay. Thank everyone for coming out, and let's thank Lenny for